Alright, hey guys, what's going on? So today we're going to be deriving the Pauli Exclusion principle from the quantized Dirac field, or the quantized spinor field. Before we do that though, I'd like you to hit that subscribe button, hit that like button if this is the kind of content that you're into. So without further ado, let's get right into the content here. So when we're talking about, so we're sort of in the context of talking about the quantized spinor fields. And these spinor fields, again, we've talked about what they look like, what the solution to the Dirac Lagrangian looked like, and we're at this point now where we've constructed a field, right? The field was this thing that was a function of space. It was also a function of time, and at each point in this field, we had spinors, and these spinors they had complex values, and they had real values, or real components, if you will. And then we had these creation and annihilation operators that we introduced also. What we're going to get at today is what the relationship is between the creation operators and the annihilation operators are. Because again, when we talked about this before, within the context of the Klein-Gordon equation, what we were aiming to do was getting an understanding of what the relationship between the creation and annihilation operators are. And in doing so, we found out how we could create and annihilate particles with these fields. Okay? So let's get into deriving the Pauli exclusion principle. If you don't know exactly what the Pauli exclusion principle is, it's basically a principle that says you can't have two electrons within the same state. Okay? This is something that's taught in general chemistry. And in sort of within the context of general chemistry, the idea is that you can't have two electrons in the same state orbiting around some nucleus, right? You always have to go up in energy levels. When you fill the bottom energy level first, and then as you go out in the orbitals of the electron, you have to go out in that direction. You can't fill any other states that are within the radius that you filled first, or the radius that is filled first, within the atom, right? So an atom has a nucleus, and surrounding the nucleus is a bunch of electrons. You can draw that here, actually. And if I were to draw that, we have a nucleus, right? And then surrounding the nucleus, we have electrons, and then we have electrons surrounding that nucleus, we have this first orbital, and then we have this second orbital with the electrons around it, and so forth. And the idea is that you can only place two electrons in one of these suborbitals, okay? And once each orbital is filled, you have to go out more orbitals, basically. So the atom's like an onion, right? So you can't put a layer where another layer is, essentially. It's kind of what's being said here within the general chemistry context. So we're going to derive that principle using the Pauli exclusion, or we're using quantum field theory today. This is going to be somewhat maybe of a long-ish video. I don't think it'll be too long because I've already pre-written everything down. So I'll just explain it as we start. So we start off, we need to define what our conjugate momentum is, right? This is something that we've established before. The conjugate momentum is the derivative of the Lagrangian with respect to the velocity of the solution, or the motion of the solution, right? And that's right here. This is something we've derived earlier, okay? So when we do this prescription, here's our Lagrangian, right? And we're just putting it into here. We're going to take that derivative. When we take the derivative, right? So the derivative, when we take this guy out in front here, this guy here is the guy that's going to contain the derivative element, not this m, right? So this is going to go to 0, this term. This term here is what's interesting to us, and we're taking it with respect to the 0th component. So this is the 0th component, right? So it's going to be gamma 0. We're going to have this this conjugate solution, and we're going to have our I in front, all right? And then we have we established this relationship earlier where the conjugate solution, or this solution here, is equal to this right here. This was something we established before, and so we get this, and we ultimately end up with this because this here, to get from here to here, we say that this is equal to the identity, and you can prove that for yourself. Okay? I don't want to get too much into mathematical details here, but this here is something that you can show to yourself also. Okay. So now, here, so what we have going on here is the momentum, what we've established for here, okay, with this guy over here. But this is our solution, right? This is our solution to our Dirac equation. And we're saying that the conjugate momentum at some point in our field, taken with the anti-commutator, or taken with the anti-commutator of our solution at another point in the field, is equal to the Dirac delta. So you have the field, right? So you have essentially what's two fields here, right? You have the momentum, and you have the solution, the momentum of the solution. You have the solution, and at one point in the field at x, and the other one's at another point in the field y, right? If x and y are the same, so in other words, if the value, or so if we're looking at the same point, right, on the field, that means this is going to go to 1, right? At all other points in the field, it's going to go to 0, okay? And then this AB is just referring to the components, right? So because if we remember, our direct solution had, I'll do it like this. There was an entry here, there was an entry here, and an entry here. The same thing's going to go for our momentum. It's going to have some internal structure to it, and that's what these A and B's refer to, right? So A and B have to be the same. So we're looking at, say, the first entry of our solutions, okay? And we are looking at also the position of where we are evaluating the solutions. So a way of picturing that, again, is you have our field, and here is x, and here is y, right? So this relationship here is going to go to 0 if we're evaluating at 2 points. The relationship is going to go to 1 if we're just evaluating at 1 point, say. So this, if x equals y, right? That's what this Dirac delta is doing here. And then we said through this relationship that we had this guy here. And essentially what this means, we can ignore the constants, right? We can ignore the constants. Essentially what this means is this relationship right here, okay? So the anti-commutation relationship between this guy here and this guy here has to be this guy here, okay? So what does the anti-commutation relationship look like? Well, it's the swapping of the order, but with an addition sign in between them, right? That's the simplest way to remember it, right? Then this is the anti-commutation relationship. We have the commutation relationship also, where this is a minus sign, okay? So now comes the dirty work. I like to think of quantum field theory calculations as being really ugly before they get really pretty, right? You can't have a rainbow without the rain, essentially, right? That's quoting from Jim Croce. Anyways, and so what we want to do is take these guys, right? So we found out here, so one's the complex conjugate of the other, so this guy's right here, and then this guy's going to be right here, okay? So we're taking complex conjugates of those, doing the same thing here and same thing here, right? So this should be the same as this, and these two guys are the same. and then we're saying that this is equal to this right here. Okay, we can get rid of the AB here, right? Because this is really just looking at the components of each, right? So the components are embedded in these guys right here. And we can essentially we can carry this over, right? We can carry that guy over. It's not really going to matter that much though, because it's really just a drag delta function on the components. And as long as we remember that we are dealing with first components all the way around, right? We're dealing with the first components of the conjugate momentum and the first components of the solution. As long as we remember that we are dealing with the first components for both of them, then we should be good to go, right? This just simplifies one side of the equation just a little bit, right? To be fair, I will just put that in here if this is something that sort of irks you a little bit. Anyways, the next line of business here is going to be to take these guys and FOIL them out, okay? And this is where it gets ugly, right? So here we go. Foiling all of these guys out, we get these individual terms, right? You could pause the video and you can take a look at all of this. It's really just, you take this guy, multiply it by this guy, right? So we have C dagger R, CR, right? C dagger R, and we have our CR. You could see how all that works, okay? All this stuff in the front we're going to deal with later, okay? So, now what I did here is I color-coded a few things, right? So what I color-coded is, here's a blue, here's blue. What's this? I'm looking at the commutation relationship already between, because we can use these pattern finding skills to our advantage, and we say, okay, we have C dagger, CR, CR, C dagger. Okay. C dagger, D dagger. Okay. That's D dagger, C dagger. D, C, C, D. And D, D dagger, D dagger, D. You could start to see how we might be able to factor out commutation relationships here. Since these are all plus signs, we're going to be factoring out anti-commutation relationships, not commutation relationships. Okay? So now, again, recall that these are what our solutions look like. Okay? And this is where we set these guys to our anti-commutation relationships, right? So I have this pink again because we have our D dagger, C dagger, D dagger, C dagger, C dagger, D dagger, C dagger, D dagger, right? So I've just said, okay, we're going to set this guy equal this. This is sort of by definition, right? This is the definition. We're going to set that equal to 0, though, okay? That we're demanding this, okay? We're setting all possible combinations of the two equal to 0, except for, so we're setting the possible combinations of the pink ones here and the brown ones here to 0, not the blue and the green ones. So the blue and the green ones, this is going to be, here's our blue and here's our green. And what we're doing here is we're going to take these guys here. So here's our blue, right here. We're factoring out the C daggers and the C's, as we're doing here, for each term, okay? And then we're just taking our exponentials and rewriting them a little bit, right? So for this guy here, we have a minus x with plus y. So we have minus x and a plus y, a positive y right here. And then the k's are going to stay the same so that the signage can stay the same. You can pause the video here to really prove to yourself that this is the case. And we're doing the same thing right here. Okay? And I try to double check myself as I was writing this out. If I have made a mistake, then please make a comment in the videos. And so, okay, Okay, so we're at this point now, here and here. So right here and here. And then what we want to do is this is where the magic is coming in, right? So because we realize we have C dagger C, C C dagger, that right there is an anti-commutation relationship. So we factor this guy out because these two guys are the same, and we have this, right? We have these two relationships. This is the blue, this is green, and we demand that this equals this, and that this equals this. Okay, this we want to remember that this is what we're demanding to be true. Okay? Now, we break things apart a little bit. So we break apart our exponentials. Okay? Break apart our exponentials. And in green here, we see here that this is starting to look like a Fourier transform almost. Right? Because this here and this here is going to give us, if I zoom in a little bit, this right here, right? Because when we take that, so this right here, this is sort of not by definition, but this is something that you can actually prove to yourself also, right? That the direct delta function of this guy here and this guy here, that's going to set k to be 0, right? Right, because when we set, we're not setting k to be 0, we're setting k to be k dagger, or you set k dagger to be k, and when you do that, this goes to 0. When this goes to 0, that goes to 1. Okay. Same thing here. So this here with this guy here, I should actually erase there and erase right there, because those guys equal 1, and I'll do that. So that equals 1, just the green guys, and we're carrying the other guys over into here, right? So we have our two exponentials and our factors. You can see here these factors are going to cancel out with each other, and what we get are these guys, right? And these are Fourier transforms, right? So the Fourier transform of something that has a particular frequency, right? The frequency, Fourier transform of that is going to be a spike at said frequency, right? Fourier transform again, spike at said frequency. We have these 1/2 signs, so a half of that plus a half of that is a whole of that, and we get that this equals this. So demanding these to be the case and demanding all other anti-commutation relationships proves or tells us that, if we go back, it tells us that we have managed to recover the Heisenberg uncertainty principle, which is this guy right here. Okay? So that's these guys right here. That's what we've demanded. So we were able to recover the Heisenberg uncertainty principle from the generalized Dirac solution. Now, here's where the Pauli exclusion principle starts to rear its head, right? Because what happens now is we take this relationship, we demanded this to be true, right? We demanded that when we take two daggers with themselves to be true, or to two daggers with themselves in the anti-commutation relationship, we have this equals 0. We have then, so this plus this is going to be 2 times that, and we divide both sides by 2, and we get this. This is weird because if this equals 0, if we act on a zero particle state with this guy first, it's a raising operator, it's going to give us 1, and then we raise it again, that should give us 2, but it gives us 0 because of this relationship. So in other words, we cannot create two particles. Based off of what we've done so far, we cannot create two particles with the same state, right? Because, again, we've demanded that these anti-commutation relationships must be true, in order to satisfy the Heisenberg uncertainty principle for spinors. And lo and behold, we have proven, using quantum field theory, that the Pauli exclusion principle is indeed a principle of physics. Based off of really just the math, a few things we've talked about in other videos, and we've shown it to be the case, right? So what I want to do in the remaining, hopefully just a few minutes, is correct an older video that someone had made aware of on Dirac, or on one of my quantum mechanics videos, right? So someone had noted, and thank you, by the way, that my matrix multiplication was a little bit off, okay? And there's another video, an older video, that I had made, I think probably last year, in the same playlist, where some of the video cut out, okay? If that's something that you want me to go back and remake, I'll go ahead and do that. I want to clear up that, I don't want to make this too long though, so I'm just going to clear up this right now. You can comment in the videos if correcting the cutout of that earlier video is something you want to see also. Anyways, the mistake that I had made was really just some matrix multiplication, right? Where we had, I multiplied these two guys incorrectly, right? So this was the multiplication that I had. What it should have looked like is this, and that actually should have gone to 0. All right, so in some cases, matrix multiplication, or the commutation relationship between two matrices equals 0. Right? Just sometimes that is the case. But other times, the point I was trying to make in that video was that sometimes it's also not the case, right? So here, right, if we do the matrix multiplication here, right, we should get these guys, and I double check these also just to make sure I was being sane on these. 0 times 0, 1 times that, so that gives us that, and 0, that should be also 0. So you can double check I did this right, okay? And what should happen is that we take this minus sign out, we get plus. By making this minus, this should also be a minus sign right here, like here, and we get 2 times this guy. Right, and so this is telling us that the commutation relationship is not necessarily 0 for other types of matrices, and that was really the point I was trying to make in there. But anyways, this was a little bit of a longer video. I hope you guys enjoyed it. Hit that like and subscribe button, and I will see you guys in the next one.